for coming and agreeing to give a talk. So Oliver is a professor at Carnegie Mellon University at the Robotics Institute. Before CMU, he was at USC doing his postdoc, and before that, he received his PhD from Max Planck, and before that, he was at University of Cambridge. So he's been, in Europe, in England, on the West Coast, and now on the East Coast. And over the year, Oliver has done a lot of fun work in manipulation, ranging from stacking blocks, or more recently using audio in audio and video for learning, some kitchen tasks. So you pretty much pick up any manipulation task and you would see some paper from Oliver, which would be worth reading. So it's a pleasure to have you, Oliver, and really looking forward to your talk. And with that, take it away.
Thank you, Pulkit, for the wonderful introduction, and thank you everybody for joining. Really happy to be here, even virtually. Obviously, be nicer to be on campus and see everyone in person. But I'm very excited to be presenting and meeting with a lot of you today. So I'm going to be talking about structuring manipulation tasks for efficient learning. This is good work that's mainly been done at my lab at CMU. So I'm the head of the Intelligent Autonomous Manipulation Lab. And our goal really is to develop robots that can work in unstructured environments. So in the future, we want robots that can work in hospitals, households, that can take care of the elderly, work in hazardous environments, and even do things like agile manufacturing and tasks we currently wouldn't really think of robots to do. But if we can create these sort of very versatile robots, that new application domains, new kinds of jobs will open up in the future. So in order to work in these kinds of environments that are sort of unstructured, we need robots that can actually be sort of robust and versatile. So robust means that either that they're reliable, so whatever skills they execute, they have a high success probability in their given domain. But it can also mean being able to identify errors, right? So if you make a mistake, if you can recover from that error on your own, that's generally not such a major mistake, rather than breaking something or having to call for assistance every time that something goes wrong. We also need to have obviously versatile manipulation skills. So these are skills that are not sort of just for one very specific situation, but that can actually generalize across different scenarios and adapt to the kinds of objects and environmental features that the robot's interacting with. So, the grand vision really is this sort of, operating in unstructured environments. And I think the key challenge there is really, how do we take that complexity and make it into something that's tractable and manageable? All right, so let's consider here a robot that's sort of trying to do some kind of a cooking task. And how do we make that a little bit more tractable? So one way of doing that is by focusing the scope, right? So the robot's going to be, surrounded by lots of different objects, lots of different things that are going to sort of distract you from the skill. But really, when we think about individual manipulation tasks, there's often only a few different objects that are involved. We often only need to learn certain aspects of the problem. And so being able to sort of autonomously reduce that scope to just those areas where you need learning and focusing that learning on the key challenges is going to allow you to create skills that are more versatile and more robust. Another key sort of tool in our toolbox is modularity. Right, so we could sort of imagine this as a single monolithic scene, but as humans we tend to sort of look at this and break it down into smaller pieces, right? So we have our two hands, they're obviously grasping different objects, the knife and the cucumber. We can have the food item there. There might be other food items nearby, so maybe we have to select which kind of food item we want to be cutting, given the current situation. But we can sort of take that complex scene and break it down into smaller pieces, and also look at sort of how we can sort of control the robot using a modular structure. The last way that we can sort of, or the last tool that we can use is interactions, right? So the robot isn't just a passive observer, it's an active agent. It can perform tasks, but it can also sort of interact with its environment to get additional sensory information. So often we look at sort of tactile feedback, for example, for identifying different kinds of objects. So it turns out this is a cucumber, these two are bell peppers, but this is actually a plastic toy that just happens to look like a bell pepper. And so by interacting with the environment, we can sort of identify different kinds of material properties. We can also detect different kinds of events. So, when we're cutting down, we want to make sure that we're not cutting too far into the cutting board and actually terminate when we make that contact. So during this talk, I'm going to be talking about these three different areas and some of the research we've done in each one of these. And we're actually going to start off in the middle here with modularity. So modularity, I like to think about as sort of trying to take a big problem and break it down into smaller pieces that can then be reused and sort of recombined depending on the situation. Now, we see actually a lot of modularity already in robot manipulation. When we think about objects, I like to think about them in sort of a hierarchical structure where we have individual objects at the top, or on top of that, you can even have collections of objects, but let's just focus on the objects themselves. You can break those down into different parts. So we have, for example, this cup has an opening, it has a handle, it has a side or a container like the volume, and it has a base. And each one of these we could break down even further into individual points. Some of these might be points that we want to make contact with or that we want to avoid. But sort of breaking the objects down to these parts provides a lot of modularity in the sense that, if we try to generalize a grasp, for example, from one object to another, rather than treating the object as a whole, we can try to find, similar types of like parts, so different handles, or, the size of the object. And similarly, we could try to find similar kinds of contact points on the object and try to generalize like that. So that's one kind of modularity we see. We often also think about skill modularity. So in terms of taking a skill or a task and breaking it down into a number of options for performing that task. So we might have a very high level policy telling us to make a sandwich, but we can break that down into smaller components. So, slicing a piece of cheese. In order to do that, we might have to grasp a knife. We obviously need to grasp the cheese as well and place it onto the bread. We need to grasp the bread. And so we're going to see there's a lot of different options in that framework where, over the course of making that sandwich, we're going to be reusing multiple skills multiple times in order to accomplish that overall task. But like I said, this is a fairly standard sort of decomposition using options. In manipulation, we also have another kind of modularity, which is that we often want to perform multiple subtasks in parallel, right? So rather than just slicing a cheese and then placing the cheese, we often want to execute multiple types of controllers in parallel. So for example, here we have a screwing task. We can break this down into two steps in a sequence. But each of these steps requires multiple controllers. So for the first one, we need to be able to reach the end of the screwdriver into the head of the screw. And we also need to make sure that the axes of the screw and the screwdriver are aligned. Once we actually achieve that part, we can go on to the next step. And there we have an additional controller, which is going to be pushing. So we want to make sure we're not just at the location, but we're actually applying a certain amount of force into the screw. We still want to maintain alignment so we can keep that part of the control architecture as before. And additionally, we want to have this sort of rotation around that axis so that we can actually screw it in. And so what we can see from this example is that often these subtasks are kind of very object-centric, right? We're thinking about the axes of the screwdriver, the location of the screw's head. And that's obviously very natural for kind of manipulation tasks. We also see that we need to have a variety of different controllers, and we need to sort of mix and match different types of these controllers in order to accomplish different kinds of tasks. So what we did in this project was to actually look at sort of decomposing these skills into single axis object-centric controllers, and then combining them into different kinds of skills. So how can we do this? So we begin with an existing library of single axis controllers. So for example, here we have this green robot block. So we can move this green block. We have an object, this red block that we're trying to manipulate. And we have a bunch of walls in the environment. So what we want to do is we ultimately want to slide this red block up to this corner, for example. Now, based on the fact that we have these objects in the environment, we can sort of automatically specify different kinds of controllers. So we can have, for example, a corner here, we can have the wall, the object in this wall, and we can have, force controllers and position controllers to try to reach them. So for example, we have a force controller applying a force to towards this object, and position controllers for moving to this location and this location. Now, in order to actually perform the task, we need to select some subset of these controllers to operate together. So if we want to move this red block up to the corner, what we want to do is we want to first choose a force control so that we make contact with that surface. But we also want to move our end effector sort of towards that upper edge or the upper corner so that we actually get that sliding behavior. So the way that we do this is by having the robot actually learn to select prioritized lists of controllers. So in this case, we have this controller first, and then with lower priority, this position controller. Now, trying to execute both of these at the same time isn't going to work very well. What's going to happen in that case is we just add up the forces and we suddenly start applying a lot more force to this object than we want to. So instead, what we do is we project this lower priority controller into the null space of the higher priority. Okay, so as a sort of classical hierarchical control, where we sort of now we can maintain the force here, and within the null space of that force, a controller, we can slide the object up to that desired location. We can do the same thing for rotations. So we, rather than sort of talking about quaternions and rotation matrices, we can have controllers that try to align different axes between the hand and the object. So we might have a high priority controller trying to get this blue axis of the hand aligned with this blue axis of this handle. And then we can also specify a second controller, which is going to rotate sort of within the null space of that, so that we still get the blue alignment, but we can still rotate around that blue axis to also align the green axis here. All right, so how can we actually use this kind of combining of different controllers? So as I said, we sort of assume for now that we have some kind of task axis controllers pre-specified. We then actually want to have a neural network predict which kinds of controllers we want to use in our framework. So which sort of choosing the prioritized controllers. We can then use this approach for combining the controllers using this null space projection to create a full skill controller, which we can then execute on the robot. It'll do that for a certain amount of steps and then sort of switch over to another set of controllers as needed. And so the core learning problem here is actually learning this, this controller selection. So we train a neural network to choose the different controllers. But one important part of that is really the action representation. So a naive approach would be to say, okay, we have, for example, 20 different controllers in our environment that are, that are afforded, and we're going to choose a combination of 3 of these. So if we take that, that combinatoric, or those different combinations, we see that we already have almost 7,000 combinations, right? And sort of treating each of those different kinds of controllers as a sort of separate entity or separate action is very inefficient. So instead, what we want to do is we want to actually be able to share information between the different controllers as we're sort of selecting them. And the way that we do that is by, rather than choosing all 3 controls at the same time, we pose it as an expanded MDP. Okay, so we effectively have, rather than choosing all 3 controllers at once, we choose one controller. We take that control that we chose, we add that to our state space and use that to choose a second controller, which we then again add to our space for the third controller. And only after choosing all 3 of these controllers do we actually execute this. So the reason that this actually works and sort of makes it more efficient is that it allows for more information to be sort of transferred between the different skills through the value functions in the state. So you can imagine that if the first controller you choose, it's simply horrible. It's moving away from the objects that you're interested in. Then you don't really need to sort of consider all the other kinds of controllers with it. You can just say, okay, this tends to have a low value, and focus your efforts exploring other controllers in that space. Ultimately, the way that we actually learn the policy is just using proximal policy optimization, or PPO. But the key insight is really this idea of sort of breaking it down and having these sort of the correct kind of action representation. We actually tried out a variety of different kinds of action representations. So one of them is the very standard, no controllers. You just predict the actions in the low dimension in the low-level end effector space. We looked at simply selecting one controller. We looked at selecting top 3 controllers just based on their scores. So this one doesn't sort of compare the different or based on which other ones were selected. We looked at the combinatoric approach where we just have a huge number of actions to choose from. And then we have our 2 approaches here where we always encode the action that we selected as a one-hot encoding. In one case, we sort of keep adding the to the same one-hot encoding. So after the first controller becomes, or the second controller becomes a 2-hot encoding. But we also looked at the sort of 3 expand multi, where we have n 1-hot encoding. So if we choose a second controller, we have 2 1-hot encodings. So we applied this to a variety of different tasks, looking both at sort of simple simulated problems, as we saw before, but also looking at things such as insertion and door opening tasks. And as you can see, we do get the high success rates with our proposed approaches. Here you can see what this looks like on the real robot for the door opening task. So it's sort of switching between different kinds of controllers, and then it can perform fairly accurately. You can actually perform this one with a single controller. So you do also get fairly high accuracy using just the one controller at a time. In some cases, it sort of learns to very quickly switch between different controllers in order to get that kind of a behavior of multiple controllers running parallel. If we look at, however, the screwdriver task, we can see that, first of all, we can generalize between different sizes of screws. And in this case, you actually do need to press down, you need to maintain alignment, and you need to rotate. And so trying to do that with a single controller at a time doesn't work as well. And also the combinatoric approach performs fairly poorly, whereas our approach still gets a high success rate. So this is kind of looking at how we can, take skills, decompose them to modular components, and then learn to sort of select them together to make those high-level skills again. Of course, we don't just have modularity in the actual policies. We can also see them in the preconditions. So the preconditions for a skill are effectively the situations in which that skill can be executed to achieve the intended effect. All right. So for me, I always think that, preconditions are very important. They're often sort of undervalued, I find, but they're very important for sort of working in the real world because they really define the scope of the skill, right? So if the robot's working in the real world, there's obviously a lot of complexity, but as long as you have an accurate precondition, the robot can kind of say like, okay, I only need to learn the skill for these kinds of situations. I only need to be applied in these situations. And therefore, there's this kind of contract there that, effectively you only need to learn a skill for those kinds of situations and to have the intended effect. So yes, so I think preconditions are very important, but they're obviously very challenging because they do present the robot with this complexity of the real world, right? So there's going to be a lot of irrelevant objects. There's going to be objects added and removed, and the robot ultimately needs to be able to adapt to these kinds of variations. So the way that we approach this is actually by looking at graph-based preconditions. So what we wanted to do is we wanted to take our scene. So here we have a robot with a knife, and we wanted to actually be able to decompose that scene into sort of pairwise interactions, and then sort of based on that graph structure, predict whether or not this scene will actually afford cutting. So in this case, generally looks good, but it will actually stab the bell pepper, so probably not actually a good skill to execute. Now, in order to learn this, we kind of want to avoid having a very large reliance on sort of real-world data. So obviously, connecting knives, stabbing to objects, it's not something that we want to have, to do a lot of. And so we want to see, like, are there ways of sort of capturing the kind of simple interactions in this environment, and then using those to kind of bootstrap this precondition model. And so the way that we did that is by actually training these object relations in simulation. So what we want to do is we want to be able to take pairs of objects, pass them through a network, and sort of get a representation of the kinds of relationships that they have. So in simulation, we can generate a variety of different primitive shapes. We can apply different kinds of actions to them and see how those actions actually affect the outcomes of those skills or those motions. So what we can then do is we can use these to actually define triplets for saying certain scenes are more similar to each other or more different. So for example, here we have our anchor triplet, which is chosen somewhere in our data. So we have an object here that's kind of above this yellow object. We have the voxel scene, which is the actual input to the network. And what we can see is that we have a positive sample here, which when we perform the actions down, left, and right, we're going to get very similar effects. Whereas if we have this object here, which is a little bit more to the right, so it's a different scene. If we actually try to move down, then we get this very large torque being applied to the object, and therefore we can actually say that, okay, this is actually a dissimilar scene, and therefore we can treat this as a negative. And so what we want to do is we want to learn a representation of these sort of voxel scenes, which is going to put this anchor and the positive close together, and the anchor and the negative further apart. And so we can do this with a triplet loss, where we take the different scenes, we pass them through our network, we learn this sort of relation or this embedding network based on these. We also look at training these embeddings so that they can predict things like the effects of these low-level actions. But ultimately, what we can do here is we learn these kinds of embeddings, which are now going to sort of be representative of the kinds of interactions that we can often see in the world. So when we actually want to now learn the preconditions, we do still want to have some real-world data, obviously, in there. So we do take our different examples. We have the robot try, for example, 25 different cutting behaviors with different object arrangements, and we can have the robot determine was that success or not. And then it can still get that ground truth labeling. But what this does is that this gives us a very nice representation of the relationships in the object based on those simulations. And so by sort of breaking it down, we get these sort of simpler interactions, which we can then use, for example, with a relational graph neural network in order to predict the actual precondition values, whether it will succeed or not. So here you can see what this looks like in practice. So here the robot's, for example, looking at sweeping skill, it has this knife, it's gonna sort of move across, and the question is this going to sweep all of the objects? So we can again voxelize that scene, identify the different pairwise relationships between them. Our algorithm says that's not gonna work. And in fact, if we do try to run it, we see that this bell pepper, is kind of out of the way. The nice thing about this graph neural network approach is that it does also sort of generalize between different numbers of objects. So we can train this on 3 to 4 objects, and we can test it on, for example, 6 objects, and we still get a very nice high F1 score. We can also do this, for example, for stacking blocks. In this case, trying to see whether we can move a black object. We have this nice structure there, and again, we can predict fairly accurately. Just keeping an eye on the time, I'm going to move a little bit faster. We can also do this, for example, for the cutting, as I mentioned. So in this case, we have this knife and the cucumber. We were grasping the cucumber, so that all looks good. But we can actually see that the prediction is from our algorithm that's not going to work, and the baseline says that's going to work. And the ground truth is that it's not going to work. So you do start stabbing another object, which obviously in the real world you wouldn't want to do. If we remove that object from the scene though, then our prediction is actually that it will succeed, and at that point we can actually perform it. All right, so a couple of key takeaway ideas from that part of the talk. So first of all, the idea of trying to compose skills from smaller object-centric controllers. So rather than thinking at the skill level, we can think of it as sort of that single axis controller level, and being able to sort of share those controllers between different kinds of skills, but also being able to generalize sort of more naturally between different kinds of objects in the scene. So I think this is very closely related to this idea of affordances and generating actions based on those simple interactions afforded. The second part looked at really at modeling the scenes as graphs of interacting objects. And sort of the key idea there really was that we can take a complicated scene, we can break it down into individual objects, individual interactions, and those interactions are often a lot easier to represent, they're easier to model, and therefore we can use something like a simulator to capture those simple interactions and then leave sort of the, the high level complexity of the whole scene to learning that from the real world. And so we can again, break that problem down to smaller pieces and then use that for more efficient learning. All right, the second part that I want to talk about is scope. So how do we actually determine what we should be focusing on when we're doing learning, or when and what to learn? So the first project I'm going to talk about is looking at patching models. So we're very interested in the idea of sort of combining model-based planners together with learning-based skills, or learning-based approaches in general, I should say. Obviously, planners can generalize very broadly. If they have a good model, they can perform a wide range of different tasks. But obviously, in some cases, you do want something that can adapt from experiences or incorporate additional information, in which case you'd want to maybe use a learned skill. And so what we wanted to do is we wanted to look at the scenario shown down here, where we have a certain space. We might have certain regions where the model might fail. And in this case, it's actually inside, our goal state is actually inside of that region. And trying to plan all the way there is not going to work. But what we can do is we can learn skills to kind of patch the problem by effectively learning a skill that will take us then from some precondition area, which we can also learn, and then bring us to that final location without relying on the model, right? So for the blue area, we can always use the model, so we can get a lot of generalization in that region, but we still have that sort of robustness there of having that additional skill, which will take us to the area that's a little bit more difficult to model. So how do we do this? So we start off, with a given model. We run a planner on it, shown here for an insertion task. So the robot's trying to insert this sort of this pink rectangle into this pink slot. Can generate different kinds of motions, assuming that model is correct. We can then execute that on the real robot, and we can detect when we actually deviate from our model. So, are there unexpected contacts? Are we at a different location? Has the object shifted? Down here, you can see some of the kinds of errors that we encountered. So, the twisting of the handle, or some kind of a translation misalignment, where the object simply isn't going where the model predicted. So what do we do then? In that case, first of all, we can use that as an example for our model validity classifier. So we want to be able to predict that the skill is not going to work in these kinds of situations in the future. But we also ask for a demonstration, all right? So often we can ask a human for a demonstration in order to actually learn a skill. And that skill is going to give us, or that demonstration is going to give us two things. First of all, it's going to give us a skill precondition. So we're, the human's going to move the object to a suitable location to start the skill. And secondly, it's also going to give the actual demonstration of the skill, which we can use to train a skill policy. So at test time, once we run this a few times, what we can do is we can now again model, take our model, generate a plan, and we can now take that trained model validity classifier and determine whether or not the skill is actually going to succeed. Oh, sorry, not the skill. The plan is going to succeed as it was planned. If our classifier says it's all good, you can just keep going, then we can actually just execute that, and that's great. However, if the classifier says, oh, this isn't going to work, there's a couple of states along the way which I think are going to break the model assumption, in which case we need to replan. So we can take our learned skill precondition model, we can actually replan a trajectory to that, and then once we get to that location, we can execute the skill policy from there. And then hopefully that'll give us the right kind of insertion. So you can see what this looks like. So this is the training phase. The robot's created this plan, it's picking up the object, and it's trying to insert it, and then it detects that there was an error. It didn't work as expected. Now a person's joysticking it with a game controller and demonstrating that's insertion skill. If we now test this, we can see that, and in this case, it predicted that, going directly for the insertion is not going to work. So it's actually going to create a plan to go to that corner area and then execute that skill from its precondition region. So here we have some of the results with and without obstacles. So we tried using just a DMP, so just learning the entire trajectory itself. We tried just using the planner, and we tried our approach of sort of combining the learning and the planning approaches together. And as you can see, we have successes, partial failures, and failures. A partial failure pretty much means that it got part of it into the slot, or that it got very close to the slot, whereas a failure pretty much means it didn't get to it, or it collided with the obstacle. And as you can see, we have a very high amount of success rate here. Even when we add obstacles, we're still outperforming the other two. And we can actually learn the skills using a small amount of data, as you can see here. So even with just 20 demonstrations, we can get a fairly high success rate. And I think that really speaks to the key idea here is that there's this nice synergy, right, where the planner, because it's able to sort of be applied to a very large amount of the state space, it really allows the skill learning to focus on a very small region, right? It's only that last sort of sliding motion that it really needs help with. And so by using the planner, we can really reduce the scope of what we need to learn, and that learning becomes a lot more efficient then. And one example I also want to mention here is this door example. So this was a case where I really love this. We had our model, we gave it to the robot, and the robot effectively just planned all the way through. So we were really expecting to have to, use some kind of a skill to open this door. But this was one of those nice situations where the robot pretty much just said, it's okay, I got this, I don't need to learn anything, I can just use my planner. So as someone who does a lot of work with learning, it's nice to, sometimes have the robot tell me that's okay, it doesn't need it. All right, so that was sort of looking at, combining model-based planning together with, the sort of this patching idea in order to learn more focused skills. Another way that we can sort of control the scope is by thinking about irrelevant objects and features. So often when we have a robot working in an unstructured environment, like I mentioned before, there's going to be a lot of objects, there's going to be a lot of distractors. Many of the things in that environment are not going to be relevant for the task, and trying to sort of learn to adapt to them is going to sort of result in very brittle kinds of behaviors, right? The kind of behavior where you're pouring and, I don't know, there's a book on the shelf, maybe, I don't know, it's in a different location today, and so you're going to pour differently, right? It doesn't really make sense for us as humans, but if, a robot just learns over these different kinds of situations, that's something that it can potentially learn. So what we want to do instead is we want the robot to actually identify what are the relevant variables and sort of reduce its network to just focus on those, right? So the way that we approach this is by having a set of skill parameters given here by theta. And these are going to be executed by a low-level controller then. So this could be, for example, a DMP or some kind of a waypoint trajectory. And we have some context variables. And a lot of these context variables are not going to be relevant as given by these sort of gray dots. And what we're going to do is we want to learn to sort of reduce that context to just the relevant ones and just have those be the input to our network. We can even go one step further. So this is sort of our reduced multi-layer perceptron. We also have what's known as a partitioned multi-layer perceptron. So this is now focusing only on these relevant ones, but rather than having all these relevant contexts mapping to all of the action parameters, we actually learn for each one of the action parameters a subset of these relevant contexts for that one. So, as we'll see, it might be that certain, the height or my amplitude in a certain direction of my motion only depends on maybe the height of the objects, but not their horizontal position. All right, so the idea is really to sort of, to determine that structure of the network for more efficient and robust learning. To do this, we're going to assume that we have a very simple internal model of the task. And I think, for me, this is really going to this idea of sort of intuitive physics. So often, we have some kind of idea of how the world works, but it's not going to be actually as very accurate. right? So what we usually do is we take that internal model, we learn some initial weights, we throw domain randomization at it, try to get something robust, and then sort of do some fine tuning on the real world. What we're going to do in this case actually is we're going to have one step before that, where we're going to be using causal interventions to try to determine what that network structure actually is using the simple internal model. So how do we do these causal interventions? So we're going to start off by sort of randomly sampling like a certain context. So for example, here we have a block stacking task, 3 different blocks. Each one of them has a height and location. And what we can do for this individual situation is we can find some task parameters theta that are going to solve the problem. All right, so in this case, the red one has to go on the blue one. We can get our thetas, which are going to give us, for example, the weight points for placing that red block on the blue block. And for that specific context, that's going to solve it. There's no idea of generalization here. It's simply solving that one specific context, which is generally a lot easier. What we can do now is we can start applying interventions because we have this internal model, right? So if we move, for example, this orange block to the side, and then internally, sorry, this is all internal, then we can sort of, see that if we were to execute the same parameters theta, we're still going to succeed, right? So we have the same performance, which kind of indicates that the X position that we intervened on is not actually relevant for this task. Alternatively, for example, we can sort of change the height of the blocks. In this case, we change the height of the blue block. And in that case, the task actually fails. It's no longer placing it on the blue block. And therefore, we can identify that the Y height is actually relevant. And we can go through all the different features in our environment and identify for which of these are actually going to have an effect on this theta and which ones are not. And we can do this also across different contexts and sort of find the ones that are more consistent. So that's going to give us from this sort of, all the context features to this reduced set of relevant ones. The next step is to actually try to identify for each one of the action parameters which context variables that one should depend on. So how do we get this sort of partitioned MLP? So in that case, we already know that the orange block is irrelevant. We can push that aside. We're going to apply another intervention. So in this case, for example, we have changing the X position of the blue blocks. And we're going to not just sort of see whether it succeeds or fails. In this case, yes, it does fail. But we're going to resolve the problem for this new context. So we changed one context variable. We resolve it to get a new updated theta, in this case, theta prime. And what we're going to do then is we're going to see which of these theta primes do we actually need to update in order to solve this task. So in this case, the waypoints, they were a little bit higher. They were definitely a little bit further across. But we can sort of find the minimum set of changes needed for that theta dashed, which actually corresponds to just going up the same height and then going back down. So what does this tell us? This tells us that this theta x variable that we've changed here is going to be relevant for the theta x, so how far we have to go across, but it's going to be irrelevant for the theta y. So we don't actually need to change the height of this based on this theta x. And so this, the x position now becomes an input to the network for the theta x, but not for the theta y. So we applied this sort of causal reasoning approach to 2 different domains. One of them was block stacking. For most of our evaluations, we focused on sort of simulations just because it's a lot easier to sort of generate a variety of different scenarios. We have this very super simple internal source domain model, which we then transfer from to the target domain. So we're doing all the causal reasoning here in the sort of kinematic domain. We also looked at sort of crate opening, and then again, passing this to the target domain in simulation. And what we see is that in general, the reduced and partitioned MLPs are more robust. So in many cases, they actually perform better on a 0 shot because they're not sort of being distracted by additional variables that can have small influences on the behavior. So in this case, for example, the partitioned MLP got 10 out of 10 0 shot. And even if we add an additional shift in the variable, so for example, changing the objects or moving the positions of the objects, we can still see that we get a very high 0 shot learning for the ones that kind of reduce that input space. whereas the ones that simply relied on domain randomization, because we had the shift in the domain, tend to be a little bit more brittle. We can also see this for the crate opening example. So obviously there's a lot of objects in here that are irrelevant. It's really about focusing on the crate. In this case, we did actually find that the reduced MLP performed a little bit better than the partitioned MLP. So some sharing of weights between the different networks does seem to be beneficial in this case. But again, we sort of saw this behavior of having more robustness and better performance when we actually use the reduced input space. And we can see this also on the real robot. So in this case, we have a robot on the left is using the full context, on the right it's using that partitioned network. It looks very similar, but as we see, because though the one on the left is kind of taking into consideration all of these different objects in the environment, it tries to sort of adjust things accordingly. It actually fails, as we saw on some of the simulation. Whereas the partition one is a little bit more focused, and therefore it has a much easier problem to learn because it's sort of autonomously extracted that structure. All right, so what are the key takeaways from this? So first of all, it's important to focus learning on the problems where it's really needed. So if we can sort of reduce the size of the learning problem, that's often much more powerful. It requires less generalization. A lot of the generalization can be handled by that planner to get us into those specific situations where we can use learning. And then by sort of reducing the scope, we can also learn more faster, for example, from demonstrations. I think it's also important to think about internal models, not just as a way of learning a skill, but really about structuring the problem. So how can we use that model to reason about the problem so that it becomes simpler when we actually try to learn it in the real world? So in this case, we looked at the relevance of features from that internal model, but there are other kinds of structures that you could potentially extract. All right, so the last part of the talk that I want to discuss is actually looking at interactions. Or how to get the most out of good vibrations, I'd like to call it. So I think one of the main ideas, already from my PhD thesis, was this idea of really having to exploit manipulation modes. So when we perform manipulation tasks, we often have these sort of discrete situations where the dynamics are going to be shifting. So for example, here we have a hand kind of moving in free space. Once we grasp an object, we can start applying forces to it. If we apply enough sideways forces, it can slide or scrape across the surface. If we apply enough upward forces, we can actually break contact, right? So we have these different kinds of contact modes. And one of the great things about this is that it provides a lot of structure, provides us some ways of monitoring our manipulations, and it actually often defines sort of goals and sub-goals, right? So if we want to pick up an object without scraping it, then this transition here becomes a goal, and this becomes an error. Whereas if we want to sort of scrub the surface, then this becomes a goal, and this becomes an error. Another great thing about manipulation modes is that they do generate vibrations often. So when you make contact, when you break contact, or when you have sliding contact, you're often generating these additional kinds of vibrations, which people can actually detect using the fast afferents in their fingers. And we obviously want to have sort of similar capabilities for robots, right? And so rather than looking at grasping, let's look at cutting. So here we have a robot that's cutting like a vegetable, and it actually has this microphone on the back of its knife. So, and also one on the side of the tongs and some underneath the cutting board. So we can actually use the vibrations detected by these microphones to detect things such as when it makes contact with the cucumber, when it starts scraping against the cutting board, and it can learn a classifier to detect those and then switch the kind of behavior based on those events. Another thing you can do is it can actually collect additional information from these mode switches regarding material information, okay? So in particular, when we're manipulating different objects, we want to be able to, adapt to the kind of material properties they have. This is especially important for cooking domains. So here, for example, as we move the knife down, we can detect that it makes contact, but we can also use that initial detection with the object to identify the kind of material it's made out of. So in our experiments, we looked at 25 different food items, 23 of which you could actually cut. So I think it was the spaghetti squash and the corn. I think those were the ones that couldn't be cut, but all the other ones could. In some cases, obviously there are very strong visual differences, but there's also ones such as the cucumber, the old cucumber. So if you're wondering, old cucumber means that, you've left it in the fridge for a week and forgot about it. That seems to be the student definition of old vegetables. And zucchini. So these three are visually very similar. We also have, for example, lemon, orange, and frozen lemon. These are also visually very similar. But what we're going to do is we want to use our this tactile vibration feedback in order to classify the different materials. So what we do is we take the vibrations from that initial downward motion, we're about 0.1 seconds. We take the MFCC, this is the Mel frequency cepstrum coefficients of that signal, and we input that into a multi-layer perceptron, very simple network, actually 3 fully connected layers, 100 units each, and the output is the classification. I do want to mention that these MFCCs, so what these are, is they are the power spectrum of the power spectrum. So you take your vibration signal, you first compute the power spectrum of them, and then you treat that power spectrum as another signal and take this power spectrum of that. So the intuition here is that you're effectively capturing the harmonic structure of that signal. So the way I like to think about this is actually as the timbre of the sound. Right? So if you hear a woodwind instrument versus a brass instrument playing the same note, you can tell obviously that they're very different kinds of instruments because of their timbre. And the same thing we're doing here, except that rather than brass and woodwind, we have cucumber and zucchini. So when we use this network to perform the classification, we can see the confusion matrix here. So this is only looking at the errors. So we get a very high F1 score of 0.99. Actually, if you look at the signals, it's yeah, it almost looks like a barcode. So it's very easy to sort of identify, even like just looking at the coefficients of what the different kinds of vegetables are. As you can see, we do get some misclassifications. So here, for example, it thought the bread was an old tomato, or that frozen lemon, or sorry, no, let's see, a watermelon was a frozen tomato. Obviously, we're not using any visual features here. We are just using that initial feedback in order to generalize and label. We can use this then to recognize different materials and then adapt the behaviors to it. So here you can see that the old tomato, we've defined some parameters that are a little bit slower back and forth movement, less pressure. Whereas with the carrot, you want to go pretty much straight down with a little bit back and forth. Some of them, you just go straight down like tofu, which is not shown here. And you can accurately classify these different kinds of vegetables. What I think is really exciting is the fact that it also generalizes to new types of fruits and vegetables. So up here, for example, we have a peach. It doesn't know what a peach is, but it thinks that it's kind of similar to zucchini. If you've ever come to a sort of underripe peach, you can kind of see what it's sort of thinking there. Here we have a pear. It doesn't know what a pear is, but apples are very similar kind of material, so it sort of classifies them as apple. And finally, here we have jalapeno peppers. Obviously, visually, these are very different from bell peppers, which tend to be a lot bigger. But in terms of the structure internally, they are actually very similar. And so the robot can sort of identify that this jalapeno pepper, although it's never encountered this kind of pepper, is very similar to a bell pepper. So looking at the kind of like representations of different food items. We looked at sort of cutting them and sort of adapting them to the behaviors based on those materials. But we also want to see whether we can kind of learn better representations of food items through this kind of interactions. In particular, the idea was to sort of have robots be able to play with food in the same way that a human would, and use that kind of interactive learning to then train to recognize different kinds of of food items and their properties. So here you can see what this sort of the data collection process looked like. We had the robot cut various different kinds of slices. We then gave it to a different robot arm, which was augmented with these sort of finger vision sensors, so we can observe the objects in the hand. We have top-down cameras for looking at it. We again have microphones on the back of the fingers, and we can perform a variety of different kinds of actions on them. So we actually sort of pick them up, drop them, we grasp them, and we sort of squish down on them. And so you can see some of the examples of the foods. This was, different kinds of cuts and everything like that. But you can also see that after we've sort of played with them, some of them became more deformed. Some of them sort of, maintained their shape. It's interesting to see, some materials, if they're very large, they kind of maintain their shape. If they get smaller, they become more deformable at that point. Some are just purely deformable, like Spam. And some, like, carrots are fairly rigid, no matter the size. You also get things such as, the peels of the vegetables, sort of maintaining some shape. We again looked at sort of using a triplet loss approach. So we looked at using, for example, the audio signal or the proprioceptive signals from interacting with these objects to identify positive and negative pairs or triplets with anchors. We again sort of, learned embedding using these. And then once we had that so self-supervised or unsupervised training of the embeddings, we could then apply a classifier on top of these using some human labels. So for example, we looked at, identifying different types of food. So in this case, we also had a baseline of ResNet. Obviously, ResNet has, from vision alone, a lot of experience with different types of food. So that one performed excellently. But if we, for example, said, okay, there's different types of hardnesses of objects, how well can we classify those? So in this case, here, this is the P, this is the proprioceptive feedback. So the embedding learned based on like how much the fingers closed during it, or how much force, or how much resistance there was on going down. This one actually got the best performance, outperforming ResNet and the other embeddings. If we look at something such as the juiciness, so we again had 3 classes, so sort of dry, very wet, or kind of in between. In this case, actually having the audio data from the playing was very useful for learning embedding that could classify these. And similarly for the slice type, we had the slice, and we also looked at the slice width, so what the finger width is between the fingers at the end, and that was sort of the best for the proprioceptive. All right. And so, yeah, that generally just shows that, through sort of the sort of self-supervised play, the robot can learn sort of better representations. Obviously, these numbers, there's definitely still room for improvement there. This was very unstructured play. So, if you press it more at the highest location of an object, or, you did a little bit more systematic interactions, I think we could actually improve this even further. One picture I always like to show here, this is actually looking at the embeddings of boiled and unboiled vegetables. So the color actually indicates the type of vegetable, and the shape of the marker actually indicates whether it was boiled or not. So we can see, for example, we have pears and apples. So pears and apples, they tend to be fairly close to each other in this embedding based on the audio data. As we saw that already before, pears and apples for the cutting were considered very similar. If we boil them, they go from over here to over here, still staying very close to each other. If we have, for example, carrots and potatoes, initially they actually are a little bit further apart. So we got the orange and the brown here, but when you actually boil them, they again have the shift to the right here. So everything is very cleanly actually separated here between boiled and not boiled. But we actually see that the carrots and the potatoes get moved closer together. And if you've boiled potatoes and carrots for about 10 minutes, you do notice that they actually do have a little bit more of a similar consistency, which we're also seeing here. All right, so the key takeaway messages from that part were, it's important to consider the kind of vibration feedback when interacting with objects. It's a very low cost information source. So, the microphones themselves are often just a couple of dollars. They have a very broad range, area that they can sort of, collect information from. You don't need to make sure you're always making contact with the sensor, because it moves through tools and the robot. And so I definitely encourage people to, explore vibrotactile feedback further, and also to think about, using interactions to get more information about objects in the environment, to have sort of this interactive learning. And so, we looked at how we can sort of take that big problem of, robots trying to cut vegetables, and how we can reduce that by, having the robot identify the scope of the problem, exploiting modularity, and ultimately using interactions to help get a lot of the more details of the scene, largely autonomously. One project I didn't cover, but I'm very excited about. This is a collaboration together with Professor Zainab Temel. So when I started off as a junior faculty, I always said I'm not going to design a gripper because I always thought that's, it's going to be too difficult for me. But through the power of collaborations, we have been looking at creating this sort of dexterous gripper. So each one of these fingers has 3 degrees of freedom based on a delta sort of a robot structure. So it's a parallel mechanism. And we can see things such as, removing a grape. I don't know why these are so slow. In-hand manipulation of a coin here after picking it up, or even, using dough to roll it. In this case, I should say that these were either sort of pre-programmed or, teleoperated examples. But I'm very excited about, in terms of dexterous manipulation, what we can do with this. With that, I'd like to thank all of my students. They did a lot of great work that was presented today. Obviously, also the funding agencies. And with that, I am at the end of my talk, and I look forward to your questions.
Thanks, Oliver. You timed it perfectly. You're right on the clock.
Oh, okay. I was okay. Yeah, with the questions.
Yeah, no, thanks for the broad overview of the knife and of the cutting problem. So let's see if anyone has any questions. Guys, do you have a question?
Oh yeah, I do have a question actually. Yeah, thanks Oliver for like the very thought-provoking, provoking talk. I really enjoy listening to it. I guess I have a few questions, but I'm going to focus on one. So I really find the idea of using microphones to detecting to be very, very interesting because I feel for tactile feedback, you do get sort of the integral part, which is sort of force sensing, but for both detecting the texture and for detecting slippage, I feel like you actually don't need a full image sensor to actually detect it. So
absolutely,
yeah. So I was just wondering, any thoughts on actually attaching microphones to replace these gel sense sensors, and maybe you can do a supervised a task of doing an object classification purely from basically rubbing the rubber tips on the object.
So I would say that they are very complementary. So I wouldn't think of them as sort of one replacing the other, but if you are doing something like material properties, then you're rubbing your hand across that material, then yes, it is a very low cost, very robust way of collecting that information. If you are looking for something very specific, so I mean with gel side, I think I've seen people looking at individual hairs and stuff like that. If you're trying to localize a hair in your hand, that might be a little bit more difficult. If it's something like a scratch or something on a surface, then you can definitely run your finger across that and get the proprioceptive information for that location. But I would say that they're very complementary. I think vibrations are also very important if you think about things like tool usage, right? So where you suddenly have to start reasoning not just about the contacts on your hand, where obviously the gel side is very strong, but also the contacts with a tool, between a tool and some other aspect of the environment. So in those cases, you still get the vibrations kind of going through the tools, but a lot of that sort of material property stuff isn't going to be captured in the image.
I actually, yeah, I was thinking about that, because I noticed that when you mentioned these vibration sensors, I feel the kind of a granularity you're at is still sort of on the end effector level granularity, but because much of our tactile sensing actually comes from the vibration sensing, which is in temporal domain. That's why we have these fingerprints, right? Because this is actually doing Fourier transforms of the local texture. So actually, when you said that, you can actually do the single hair with a gel sense sensor. I was actually thinking that no, I can actually do that with basically 3 microphones, and I can do basically phase differential between the microphones as basically sort of a low level hardware. And then provide that an imaging capability. Yeah, so I feel this is actually viable technically. So basically, to summarize, I can actually detect single like hair between two like fingers by having like a multiple like microphones and like use the phase separation between the different microphone pickup to like triangularize things, and then by actually having like these like fingerprints on the fingertip. So I think that's actually potentially like a route for a new sensor.
Okay, nice. How important though there's the I mean, you know, you're moving your fingers back and forth. I mean, I guess that is still something that you need in there then, right? That like
Absolutely, and that's what we do.
Yeah.
So like two relevant things. One thing is that like when Apple designed like the trackpad, they actually specifically like sandblast it to a specific like a texture so that like actually feels the same as like feels good. So that's like kind of like why like and the second thing is that in songbirds, the like the auditory like neurons do not have myelination, and that is so to slow down the neural like basically the propagation of neural signals. It's highly specialized. And it's conserved across like reptiles like crocodiles and like songbirds and birds in general. So basically like the face detection is actually something like pretty built in. So
okay, nice. Okay. Yeah, maybe we should talk a little bit more about that sort of offline later. I think there might be some
absolutely
good potential for collaboration there.
Yeah.
Well, I think that's all the time we have for